4.9 watt hours. Your numbers will be slightly different. I'm just showing that's how we get the part that goes on top. Part that goes on the bottom is what we do on this side. And now again, if this was 100% efficient, then it would be exactly the same amount of energy. We'll find out that it's not going to be. But all right, so how do we do this? This is really simple, you guys. If you look on the bottom of the hot pot, you don't have to follow me, I'll be right there.
Okay.
You look on the bottom of this, you can't really see it because it's imprinted, and it's not, it's imprinted where, God, I can barely see it. Somewhere on there, imprinted right there, is 600 watts. And what that means is that this thing puts out 600 watts of electricity in 1 hour. Now, so 600 watts per hour, that would be really easy. If we had the thing turned on for an hour, we would know how much electricity we used. But it's not turned on for an hour. We're going to have an answer in minutes and seconds. Let's say 5 minutes, 13 seconds. We have to figure out, all we have to do is figure out what part of an hour that is and multiply it. So the watts put out by the hot pot times the percent of an hour that it takes. So we have to figure out what percent of an hour 5 minutes and 13 seconds is. And then we multiply that times 600 watts. That's going to tell us how many watts to put on the bottom of this equation. So, well, how do we do that? Since this is minutes and seconds, if it was just minutes, you could divide your number of minutes by 60. That would give you a percentage, right? Like if it was 30 minutes, that would give you a half, like a half hour. If it was 15 minutes, that would give you a quarter. This is broken into seconds, and so we actually have to do it a little bit differently. Percent of an hour is your number of seconds divided by the number of seconds in an hour, which is
3,600?
3,600, yes. Sorry, I thought you said 600, and I wanted to pretend that you hadn't said that and move on. Okay. Anyway, 3,600 seconds. Right, so, all right, so 5 minutes and 13 seconds is 5 times 60 seconds, 300 seconds, plus 13, 313 seconds. So, 313 seconds divided by 3,600. Somebody want to do that for me? Please. I just drew on my shirt. Luckily, black marker on a black shirt. I can live with that.
Wait, how'd you get 3,600?
Well, that's how many seconds are in an hour. Right?
11.5.
11:35?
11.5.
Well, 11.5, that makes more sense. Okay. So that's after you multiply by 100 though, right?
No.
Yeah. So you would get, as an answer, you would get 0.115, and then to turn that into a percentage, you would multiply times 100, and that gives you 11.5%. Okay. We're almost there, folks. I know that this is sort of a complicated set of calculations, but really, taken one by one, they're not that taxing. All right. So remember, our goal, let's just don't lose track of what the goal is, which was we want to multiply the number of watts put out by the hot pot, which is 600, times the number of hours that it actually takes to get it, that temperature. And if it took this amount, it would be this percent of an hour, 11.5%. And so you would take your 600 watts times 11% or 0.115. And if I could ask you one more time to do one more calculation for me, or somebody else.
Oh, I'm gonna find. Want me to do it?
Please.
600
times 0.115.
$69.
69 what? What's our unit that we got here? Remember what we're trying to get? We're trying to get
Watt hours.
watt hours. Yeah, 69 watt hours. Okay. All right. So, again, not losing track of the goal, this whole series of calculations is to get the energy that went into the system. So what we really just calculated is that over the course of 5 minutes and 13 seconds, 69 watt hours went into this system, and the output was 34.9 watt hours worth of heat into the hot pot. And so now the last thing is to just calculate our energy efficiency. So it would be 34.9 output divided by 69 watt hours input times 100%. What would that be? Stay with it, Eric. You can do this.
197.
Say what now? 34.9 divided by 69 and turned into a percentage.
69 times 100.
Yeah.
50.57.
Okay.
58.
50 point, I'm going to do this in better color.
50.6.
50.58%. So about 50% efficient.
Just round it to the nearest
Hold on,
100%.
no, but
100%.
you just rounded differently.
What
Because
did you
before
get?
you forget it.
You sure?
Yeah.
Okay. I was, well, anyway. So, okay, folks, so it's 50% efficient because, look, let's just go backwards here. I can see a lot of people got confused, but especially the people that are confused, stay with me because there's two ways to respond when something's confusing. One is to give up, and one is to stay with it. Hello, Mr. Lighty, how are you? Nice to see you.
Just a real quick question. Your advisory is seniors
Juniors.
on this list.
I noticed that. I looked through it. I didn't see
Yeah,
myself on
okay.
there either.
I got one.
Thank you very much. I appreciate it. All right, folks. So seriously, stay with me here because let's go back to what we were trying to do. We're trying to find the efficiency, which is the energy output, the heat that is in the water, divided by the energy input, which is the electricity. Honestly, I know it's a lot of steps, but really, if you break it down, calculating the calories was easy. Converting to BTUs is mathematically possible for anybody. Converting from BTUs to watt hours, again, just a simple arithmetic calculation. Done. You get an answer in watt hours. That's the top of the problem. The energy in the hot water. Top of the problem. Divided by the energy input. This one, oddly, for me, is easier because all you're really doing, you take the wattage of this device. The hot pot puts out 600 watts an hour. And all you have to do is figure out the percentage of an hour it was. This, for some reason, is the part that loses people. Which, it's really just what percent of an hour is 5 minutes and 13 seconds. It's really, none of these steps are very mathematically difficult. Figuring out the percent of an hour, 11.5% of an hour, which 5 minutes and 13 seconds is. It's just, you know, simple math. 313 seconds divided by the number of seconds in an hour gives you 11%. You can see that anyway. It's almost 10% right here. But anyway, okay, that's fine. And then you divide them by each other. You turn it into a percentage. That's the percentage efficiency. So it takes 50% means that it takes almost twice as much energy put in, right? 69 compared to 34.9. That's almost 70. That's almost 35. That's almost 2 to 1. In other words, again, just looking at the second law of thermodynamics, it takes more energy in. There's energy lost in this process all sorts of ways in all sorts of places. Energy out the side, energy out the top, all sorts of energy lost, energy inefficiency here in the coils, some energy lost in the electrical line. But the point is, that's what we're doing. And I know that this is a little bit painful, but the idea is that you really can follow these numbers somewhere and get an answer that goes from something that you might not have understood before to something that you can actually figure out yourselves for almost anything that you use. All right, so I'm going to stop torturing you guys. What I'm going to do is I'm going to put you in lab groups and have you work through this one time, do the calculations, and then tomorrow I'll take you through what the lab report requirements are. Okay? Thank you.